Okay, let's welcome everyone. We're starting the session. Let's thank Adam Wills. He's going to present his work on efficient algorithms for all port-based teleportation protocols. Adam, the floor is yours.
Can everyone hear me okay? Not too loud, not too quiet? So thank you very much to the organizers for organizing everything. Thank you for having me. Thank you most importantly to my collaborators, Min-Hsiu and Sergei. So we're going to talk about port-based teleportation. If you've never heard of that, we're going to start by going through it in full. It's a generalization or, well, it's not a generalization. It's a different type of quantum teleportation that does something truly unique. We'll talk about the past work and then some of the work that's happened recently, of which there's been quite a lot. And then we'll finish with going over our algorithms quickly, but we won't focus too much on that because the next talk's also about PBT and there'll be more detail on the actual algorithmic implementations there. So let's start by going all the way back to original quantum teleportation. So this is a 30-year-old primitive now, hugely influential, and it allows you to send a qubit in its most basic form, send a qubit to a distant receiver, and it allows you to do that every time, and it allows you to do it perfectly. So the teleportation fidelity is 1, so it's faithful, and success probability is 1, so it is deterministic. And the basic premise, as we know, is Alice and Bob start by sharing some entanglement, so let's just say they share a Bell state. And Alice then has the qubit she wants to send, and she performs a joint measurement on her qubit to send and on her half of the Bell state. So in particular, she does a Bell measurement. She then communicates the outcome of that Bell measurement to Bob via some classical channel. And then Bob receives it, and conditioned on the outcome, he does some form of corrective unitary. In this case, the corrective unitary is a Pauli matrix. So, this is all very familiar, and we can kind of boil this down to its essentials and say A and B share some entanglement, A does some measurement, they do classical communication, and then Bob does some corrective unitary. The question that PBT answers is how well can we teleport if Bob doesn't do a corrective unitary? And the answer is actually we can still teleport really quite well. You just need slightly more general notion of a measurement, and you need to share a bit more entanglement, but you can still teleport really well. So this question was really answered in its current form for the first time by these two guys, Ishizaki and Hiroshima. They had 2 seminal papers, one in 2008, one in 2009. This is the one in 2009, which is, I suppose, the most relevant one to us right now. The idea is, so they replace these 4 steps. The first step is Alice and Bob share some 2n qubit entangled resource state. So they each hold n qubits, which we call their ports. So Alice holds n ports, Bob holds n ports. We'll go on to talk a bit more about the actual form of this resource state, but for now, let's just say they share a lot of entanglement. So Alice then performs a measurement on all her n+1 qubits. She has n ports, and she has 1 qubit to send. And we're going to allow her to do something even more general now, so she can do any POVM. And we'll go on to talk about exactly what type of POVM we want here. She then does classical communication, which in this case is some outcome from 1 up to n. And Bob then receives this information, and instead of doing some corrective unitary, as I said, we want to not do a corrective unitary, he looks at his ith port. So he looks at the port corresponding to the outcome of the measurement. Now, Bob has to do something. He can't just do nothing, because that would violate no signaling. But we allow Bob to do something which is like not a unitary or like not really any kind of non-trivial quantum map at all. He just looks at the right port, and that contains the sent qubit. Now, being able to do this is quite powerful. This has a feature called unitary equivariance. So imagine long before teleportation happens, long before Alice teleports the state chi, imagine Bob performs a single qubit unitary on every one of his ports. So Bob hits every one of his ports with U. It then turns out that when Alice teleports the state chi, Bob receives the state u chi. And the significance of this is that the time ordering of the preparation of the state chi and the application of u have been reversed. So normally, obviously, if you want to get u chi, you prepare chi and then you apply u. In this case, we've prepared u chi by applying u and then preparing and teleporting chi. And this should feel a bit icky. And indeed, it is icky because you're not allowed to do this perfectly and every time in finite dimensions. There is a no-go theorem to this effect called the no programming theorem from Nielsen and Chong. And so we want to do this in finite dimensions. We want to do this with a finite number of ports, so a finite n. And so we have to give up something. And this is kind of what the power and the problem with PBT. So the power being the unitary equivariance, we have to give something up. So we're either going to give up the faithfulness or the determinism. So in particular, we're either going to give up the ability to teleport the qubit perfectly, or we're going to give up the ability to teleport the qubit every time. And this is what defines our two main regimes. So the first is deterministic PBT, DPBT. In this one, teleportation is deemed to have succeeded every time, but the qubit is teleported imperfectly. So it's a little bit messed up at the other end. So the teleportation fidelity is slightly less than 1. In probabilistic PBT, we don't succeed every time. So the protocol does fail sometimes, but we want to teleport perfectly when we do succeed. Sorry, this is what I've just said. So DPBT, teleportation always successful, but the fidelity falls below 1. And in PPBT, it sometimes fails, so the success probability is below 1, but upon a success, perfect teleportation. So within those two cases, those are our two main areas of PBT. Ishizaki and Hiroshima studied one further choice of 2 cases each to give 4 total kinds of PBT. And those have to do with the resource state. So they ask, in one case, let's make the resource state be maximally entangled. So it could be n bell pairs. So maximally entangled to n qubit state. And in the second case, let's let the resource state be absolutely anything, and we'll optimize it. So these 2 choices give, as I mentioned, the total 4 different kinds of PBT. So in the columns, you choose either deterministic or probabilistic, and in the rows, you choose the resource state. So in the columns, you want to optimize the teleportation fidelity on the condition that the success probability is equal to 1. And in the other column, you want to maximize success probability conditioned on a perfect teleportation when we succeed. And then in the rows, in the top row, we are just optimizing the POVM. And in the second row, we are performing a joint optimization of the POVM and the resource state. And Ishizaki and Hiroshima were able to, with I think quite a lot of patience, solve these optimization problems analytically, which I think is kind of astonishing. And it's very impressive paper. And it turns out that the best you can do is as follows. So in the case of DPBT, where you're trying to maximize teleportation fidelity, you can either, if you use the maximally entangled resource state, you can get a teleportation fidelity of 1 minus something like 1 over n. And then if you're allowed to optimize the resource state as well as the POVM, then you can get teleportation fidelity something like 1 minus 1 over n squared. And then for PPBT, we get success probability 1 minus something like 1 over square root n and 1 minus something like 1 over n respectively. Notice that in both cases of DPBT and PPBT, we get a quadratic improvement in the deviation from 1, both times when you go from a maximally entangled resource state to a general resource state. This is maybe unintuitive because you would think that you share more entanglement with someone, you should be able to teleport better, but it turns out that actually having a sub-maximally entangled resource state, you can teleport better. The other thing to notice is that as n, so the number of ports, goes to infinity, both f and p go to 1. So in the limit of n to infinity, we're doing the thing that I said wasn't allowed in finite dimensions. So we're doing port-based teleportation faithfully and deterministically. And of course, that's okay because no programming only holds in finite dimensions, and n to infinity, it means we're going to infinite dimensions or approaching infinite dimensions. So Ishizaki and Hiroshima, they solve this kind of information theoretic problem, and they give us the optimal POVM and optimal resource states. Now, while the expressions for the POVMs were relatively simple, it's kind of non-trivial how to actually implement them efficiently. Of course, they can always be implemented in time exponential in n, but implementing them in time poly n, or gate complexity poly n, I should say, is non-trivial. 2023 saw an explosion in this area. I can't really account for this. Maybe somebody else can. But this was open from 2009 all the way up to 2023. And there were two simultaneous works that solved this for the DPBT cases only. So one from Patrick Hyden's group and one from Maris Dmitry and others. There was also a related work posted simultaneously as well, doing something very, very similar, but not exactly implementing PBT. I should say that between 2009 and 2023, there was a lot of interesting work done on PBT besides. So there were generalizations to qubits. There was this thing called multi-port-based teleportation to like send more information simultaneously. But this brings me to our contributions, which is, as the title of the talk suggests, to tackle all the cases. So both DPBT cases and both PPBT cases. We also get some complexity theoretic improvements. So we show how every single one of these, relative to the previous implementations of DPBT, we show how to do it a bit faster, so polynomially faster. And then separately, we show how to use exponentially fewer ancillas. So we have two different versions of every protocol, one which is faster and one which is more efficient in the number of ancillary qubits. The caveat is that ours only works for qubits, whereas the other papers address the qubit generalizations. But in the talk immediately following mine from Dmitry, he'll talk about their second work on the topic, which ties everything together. Same or slightly faster complexity improvements, and it addresses all the cases, all for all the qubits. So I can give a brief overview now of our algorithms. So we want to implement these POVMs. So imagining that our n POVM elements are these pi I, the standard approach to implementing a POVM via familiar things like unitaries and projected measurements is this operation. So called like a Naimark operation or maybe a Naimark unitary. So we attach an n-dimensional ancilla, and then we perform this operation. And then we projectively measure the ancilla. And you can see fairly quickly that that's going to give you the, that you're going to get the outcome I with the probability you would expect of a POVM, and that you're going to get a post-measurement state that you would expect. The problem is that while we are guaranteed that there exists a unitary doing this, actually implementing it is non-trivial. But we start going about doing that with our technical contribution, which is to be able to diagonalize all of the POVM operators. So in all four cases, we diagonalize all of them. And then having established what the eigenbasis is in every case, we show how to rotate from the computational basis into the eigenbasis of all the POVM operators. The reason that's useful is because it allows us to do this thing. So remembering this exactly is what we want. We want to make that and then measure I. What we do is we attach another one qubit ancilla, and we do this operation. And the way we do it is we rotate into the eigenbasis of the POVM operators, attach the eigenvalues, and then we rotate back. But the problem, of course, is just attaching the eigenvalues is not a unitary operation. And so we essentially attach the eigenvalues in this R equals 0 space and then rotate all of the junk, everything we don't want, into the R equals 1 space. And that gives us this scaled version of what we want plus junk in the R equals 1 space. And then what saves us is that we have oblivious amplitude amplification protocols that we can then boost the R equals naught subspace and get just exactly what we want left over. This is a reference to the QSVT paper. As far as the diagonalization goes, what's quite nice is that it turns out there is one framework within which you can diagonalize all 4 cases. So all of the POVM operators for all 4 cases. In order to get there, what we do in our paper is we think about qubits as spin half particles. So of course, being 2-level quantum systems, we can think of them as spin half particles. And then the natural thing to do is to imagine their spins coupling. So 2 spin half particles can combine to give a spin 1 particle or a spin 0 particle. And when you do that, you naturally come up with this like simultaneous spin eigenbasis called the Shor basis. And these basis elements look like this, where you have different eigenvalues for the joint spin of various sets of qubits with lots of multiplicities and other things. But once you've got that, it turns out that all the POVM operators can be diagonalized with relatively simple linear combinations of these Shor basis states. The reason that's then convenient is because we can then use this thing called the Shor transform, how to like efficiently get from the computational basis into this coupled spin basis has been extensively studied. And then to actually get to our eigenbasis, it then only requires some simple steps on top of that. And this is very convenient for us because then we can leverage previous work on implementations of the Shor transform. So in particular, we can use one implementation of the Shor transform. This is called the BCH Shor transform for Bacon, Chong, and Harrow. And that gives us the very fast algorithms for PBT. So one version of every protocol uses this very fast Shor transform. And so we get these polynomial time complexity improvements. And then using this Shor transform, this is called the spin coupling transform. We can use that to get algorithms for PBT that use exponentially fewer ancillars. So that's the origin of the 2 different versions of the PBT protocols. Thanks very much. Please send me an email.
Oh, well, okay.
Yes,
come in.
Okay, thank you for your very nice talk. I have a question that you mentioned in previous works, compared with the protocols using n-bar state or a general quantum state. It will have a quadratic speed. The performance will have a quadratic. So, and you said that from the entanglement point of view, it seems n copies of bare state are already the maximally entangled. So are there any studies from other resource theory point of view, which quantity can be used? So why? So compare with the n-bar state and the optimal state, are there a difference from the resource theory point of view?
So if I understand your question, so you're asking, have people looked at more general resource states and like exactly how much entanglement will get you?
Or maybe other quantities like in fault tolerance, they use magic or other things to quantify this state.
I don't believe anyone's looked at that, no. It is an interesting question. I mean, like one of the applications of PBT is to non-local quantum computing. And I could imagine it being interesting to look at, magic or other sort of interesting information theoretic quantities that allow you to do this non-local quantum computation better or worse. And the answer, I don't think anyone has looked at that.
Okay, thanks.
Thank you for the question.
Thanks for a very nice talk. Maybe just a follow-up question to that. What's the special properties of these states that are not maximally entangled that you said has a better performance than sharing n-bell state?
Oh, I wish I knew. I wish I knew. I don't believe anyone has quantified any special properties of them.
Do you know what the forms of these states?
If you look at Ishizaka and Hiroshima's paper, it's in there, the one I referenced. So okay. In there you'll see the form of the resource states. One thing that I will mention is that in our work we don't look at implementing the resource states. So like, how do you actually prepare these optimal resource states? The reason we didn't do that in our case is because the resource states are relatively simple, and it's, I think, fairly clear in some of the generalizations to QDITs and other things. It is quite a lot less clear how to prepare these things efficiently. And so in that case, I think in the work you're just about to hear about, they do look at preparing the resource states because it's very much non-trivial in that case. As for what special properties they have, sure.
And I don't know, maybe it's relevant to you or your talk. Has anyone think about mixed states as resource states?
Mixed states as resource states. If I'm remembering correctly, they show in this one that it is optimal to use pure states.
States feel the product.
No, some crazy big entangled thing. Yeah.
Okay. Thank you for the very nice talk. So do these resource states depend on the state that we're trying to teleport? So during the optimization, do we need to perform a hard average over all the states of the qubit?
Exactly. Thank you for bringing this up. This was something I tried to pull the wool over your eyes because it's quicker and easier. But yeah, when I say we optimize teleportation fidelity or success probability, and I said we just optimize that, of course, yeah, that would depend on the input state. So what we're actually doing is optimizing the Hsieh average over all input pure states of the F4P. Thank you for the question.
Thanks so much for the talk. So you mentioned that the polynomial improvement and the ancilla count improvement were separate. Are they provably mutually incompatible, or is it just not known how to get both of them at the same time?
Just not known how to get both of them at the same time. Yeah, I genuinely don't know. The natural thing to look at first would be to look at implementations of the Shor transform. The reason that you have these two versions of the Shor transform are like, essentially you look at these spins in a representation theoretic way, and then you want to like pack representation theoretic labels into qubits, and you can do that very space efficiently one way. But if you don't do it that way, like pack it very efficiently into what's called the Yamanouchi encoding, then Bacon, Chong, and Harrow show like how to do large parts of their algorithm in like high degrees of parallelism to get faster. But in that encoding, it's not clear to me at all how to do it more space efficiently and more time efficiently. Who knows? I mean, there is no like necessary reason that these complexity theoretic bounds of how fast and how space efficiently we can do it. There's no particular reason I have for thinking that's the best we can do. So it's definitely an interesting thing to keep looking at.
Thanks.
Super weird. We'll get started. Now we thank Dmitry Grinko. He will present.
Can you hear me? Oh, okay, nice. Yeah, thank you, Martin. Yeah, so I'm going to present our work, joint work with Adam Burchardt, who is also actually here in the audience. So please don't hesitate to ask him questions. And my supervisor, Ozols. Yeah, so thanks, Adam, for a nice talk. He set the stage very nicely, so it's less work for me. But the plan for my talk will still be like this. I will have the first part, a very short summary of port-based teleportation. So hopefully you already understand a lot of the context of the setting. And next, for most of the talk, I will spend describing our construction in quite some detail. And unfortunately, I won't have time to make sure that all of you understand if you've never seen the maths needed to understand such things before. So please bear with me, and hopefully the high-level picture will still be clear. Okay, so sorry, yes, yes. So let's start with a brief overview of port-based teleportation. So yeah, we all know standard teleportation protocol, which schematically looks like this. So yeah, at the top we have Alice, and this wire belongs to Bob. And in standard protocol, Bob needs to apply some non-trivial correction operation based on the outcome of the Alice measurement. So the port-based teleportation, which was introduced by Shizak in Hiroshima, avoids this non-trivial correction operation. And instead, what Bob needs to do is just to select the port, as Adam explained in the previous talk. Yeah, but the cost of doing this is that now you need to share n ports, or like n EPR pairs in this case, and you will not achieve the perfect teleportation for finite n. And originally, in the paper by Shizak and Hiroshima, this was presented actually as an example of approximate universal quantum processor. So quantum processor is like a device which takes a description of a unitary in the quantum state and produces a channel which implements this unitary. And how you can use port-based teleportation for this? Well, Bob just needs to take this resource state and just needs to apply a unitary which he wants to encode in the state into here, like u to the 10 to the power n. Yeah, and then this whole state will describe the program for such unit. So yeah, some terminology. So the psi is called, as I said already, a resource state. So those wires here which share the entanglement are called ports, and D will be a local dimension. So it's a dimension of the system A bar which Alice wants to teleport to the Bob side over here. So we are going to talk about optimal port-based teleportation. So we need to introduce some figures of merit, which we would like to optimize. And so more precisely, we can think about this protocol as some quantum channel, and from A bar to B bar. So what is going on here is that this E represents a measurement which Alice implements here. And we assume Alice has n outcomes, but potentially there might be additional outcome which will indicate a failure. So like the k equal to 0. And so in principle, we will assume that this channel is actually not race preserving. And yeah, because of this, we have two quantities which we care is entanglement fidelity, which is defined like in a standard way like this. So yeah, you should imagine that there is a reference wire system, and you plug in the EPR state between this reference and A bar. And yeah, you would like to see what is the overlap at the end of the teleportation with the same EPR state. And average success probability is basically probability of Alice not observing the zero outcome, the failure outcome of the protocol. And so these two quantities gave rise to two main types of port-based teleportation, as Adam explained already. So yeah, we have deterministic and exact, which is sometimes just called simply deterministic PBT, or probabilistic exact, which is just simply called probabilistic PBT, PPBT. And as also Adam said before, we can choose different resource states. So the most natural choice is to choose n copies of EPR pair or some complicated optimized. So yeah, this is exactly the same table, basically, which you have seen already from the previous talk. And yeah, so the colors here correspond to different measurements. So it turns out that all those different types of PBT have different measurements. And actually, this two has the same measurement. This has another measurement, and this has the third measurement, which is optimal for it. And this was already understood some time ago, all those optimal measurements. And it turns out that the pretty good measurement, which we also call standard, a pretty good measurement, or simply standard PGM, which is in this box, correspond to this box over here, is actually kind of the main ingredient for our construction. So we'll focus on it later in the talk. And yeah, as I said, analytical implementation, analytical calculation was done some time ago, and how to actually implement this. So, and in order to answer this, we actually need two main ingredients. We need to understand mixed Schur-Weil duality, which is a generalization of standard Schur-Weil duality, and representation theory of partially transposed permutation matrix algebra. So in this talk, I won't have time to properly explain those concepts, and I will and refer you to our previous work, which was presented at QAP, where we described these two main ingredients, and also a relevant other paper by Nguyen, who also described this mixed Schur-Weil duality ingredient in his paper, also at the same QAP. And yeah, before I go to low-level details of the construction, yeah, let me quickly cite all those already by now classical results, which develop a full analytical understanding of those PBT protocols. And yeah, let me briefly comment on those more recent papers. So yeah, so our work where we developed those tools for mixed Schur-Weil duality, we already in this work we presented as an example application of those and optimal construction for PPBT for optimized resource state, which is the standard PGM. And also simultaneously there was a paper by Hsieh, Timmerman, Hayden, which described a different approach for deterministic PBT, actually via block encoding techniques, similar to what Adam had in his approach. And also, yeah, independently, there was a paper which focused specifically on all port-based teleportation protocols for qubits, which also use block encoding, as you have seen. And our current work basically aims to kind of close the gap. Yeah, I'm sorry. Let me maybe use this. Right. Yeah, okay. So our current work aims to kind of unify all those measurements and present a unified perspective on implementation of those measurements in completely arbitrary local dimension. We also provide much better complexity upper bounds compared to our earlier work from September, and it's slightly better upper bounds compared to Adam's work for qubits. And a distinctive feature of our approach is that we don't have any block encodings, and in this sense, we have much simpler quantum circuits, which you will actually see with your eyes. Okay, so let's go to the main results. Basically, the statement of the main result is as follows. So all measurements for deterministic and probabilistic protocols have the following gate complexities. So you can implement them with this gate complexity n to the second power times d to the fourth power up to polylogarithmic factors in n, d, and 1 over epsilon, where epsilon is the precision. And but depending on the different encoding which you choose, how to compress basis of irreducible representations, which appear in that context. You can have either standard encoding, which achieves actually a linear time for like linear depth, basically, but it has the cost of n log n additional auxiliary qubits, which you need to use. On the other hand, if you use Yamanuchi encoding, similar to what Adam had in his paper, you will have n square actually time or depth complexity, but you will get rid of this n factor in the space complexity. You will need only have log n auxiliary qubits. Okay, so this is a statement of the main result, and now let's dive into how we achieve this. So this is the summary of all those different protocol types. And so I would like to introduce this notation for different POVMs. So we have the standard PGM, which is just E. Then we have this POVM for deterministic port-based interpretation, this E hollow star, and this E star, which is this EPR PPBT POVM. So the main ingredient is actually the standard PGM. So which originates. So the reason why it actually appears in this context is because if you write the optimization problem for maximization of entanglement fidelity, you'll actually end up in maximizing some quantum state discrimination problem. And because of the symmetry, you can show that actually pretty good measurement for that set of quantum states which you try to discriminate is actually optimal, and that's why it kind of appears in this context. So what you see here is, so you have this effect outcomes EK, which are basically, you should think about about them as conjugated states rho k, and the state rho k is like a maximally entangled state between case system and n+1 system. And n+1 system is actually exactly the system which Alice tries to teleport. And so this pi is like a cyclic shift operator, and this sigma n, this is my notation for a normalized projector on TPR pair between n and n+1 system. And it turns out that actually the optimal measurement for deterministic port-based using the standard PGM can be also written like this. So you kind of evenly distribute this failure outcome E0 among non-failure outcomes in the deterministic version. Yeah. Okay, and you may ask, what about E star? How does it look like? Is this kind of standard computational basis? Okay, so I will not give you an answer. Instead, what I will try to explain is actually how to look at those measurements in the other basis, which is more suitable, which takes into account the symmetry of the problem. But in order to do this, I need to do a quick recap on Young diagrams and mixture-while duality. So recall that lambda is a partition of an integer n, written like this. If all those lambda I parts are non-negative and they sum to n, schematically we represent partitions by Young diagrams like this. So we also can talk about the length of the Young diagram, or like length of this tuple of integers lambda 1, lambda k, if you wish, and or equivalently, it's the number of rows in the Young diagram. It turns out that in representation theory, those Young diagrams are very important, and they label the reducible representations of symmetric group and the permutations, or like symmetric group acting on qubits. So you see this kind of CSN hat. So this is like a reducible representation of symmetric group algebra. This AN hat D is set of reducible representations for a kind of matrix version of the same algebra. I would also need to use this notation for addable cells of the Young diagram. So the set of addable cells is like a set of positions where you can add a box to Young diagram such that the new diagram lambda cup A is actually a valid Young diagram or a valid partition. And what will also be important is a subset of the set of addable cells where if you add a box, the resulting Young diagram has length still at most D. And so as a second ingredient to understand our construction, we need to look at the representation theory of matrix algebra of partially transposed permutations. So it's basically like you just take a permutation on n+1 system and you partially transpose the last one. You can see it as a commutant actually of this U tensor n U bar action. And yeah, this appears in the mixture well duality. And it turns out that the ERAPs are labeled by pairs of Young diagrams. Yeah, for this specific case, the second Young diagram can be either empty or have one box. And as I said, this is very compressed presentation. All the details can be found in our previous paper. And what's important is that we use a very specific basis, which is called the Gelfand-Zetlin basis for these reducible representations, AN, 1. And again, I will not have time to explain this, but you will see an example how it looks like later. So now I can return to the question how to actually represent this E star measurement for the EPR PPT. So it turns out that we can actually unify all PPT measurements in this form. So we can introduce this G operator. We can take the measurements, measurement effects for DPBT and conjugate it like that, with the condition that this G comes from actually partially transposed permutation algebra. But it's like not like a generic element of this algebra. It actually commutes with the subalgebra of just permutations on first n systems. And it's quite strong condition actually. And it turns out that this matrix is diagonal in this Gelfand-Zetlin basis for this algebra. And you should think about this G matrix that it kind of decomposes into blocks labeled by these big lambdas, where these big lambdas are reducible representations of this partially transposed permutations. And just as an example, if we return back to those three measurements. So for deterministic PBT, those G lambda matrices are basically identity. So that's how you can kind of parameterize them. For optimal PPT, which is a standard PGM, these G matrices look like this. For some of the ERAPs, it's 0, but for some, it's full identity. And for this last one, which is for this E star measurement, which is the measurement for EPR PPBT, it looks like this. So now you don't have a full identity for certain ERAPs, but you have kind of some diagonal matrix which has positive entries, which can be strictly smaller than 1. And so in this sense, this measurement, this last measurement, is kind of the most general measurement. And with our framework, we can basically treat all of those uniformly, and we can implement it for arbitrary measurement, which has like efficiently implementable G matrix. Okay, now I want to explain how you actually do this. And for that, I just focus on the standard PGM measurement for which, yeah, this G matrix has this middle form. So it turns out that if you go into the Gelfand-Zetlin basis, constructing an armag dilation explicitly is doable thing. So how you could see that? Okay, so you don't need to understand all the notation here. So the high-level idea is follows: if I take effect and write it in the Gelfand-Zetlin basis, and you can write it very nicely as a sum of the projectors onto orthogonal vectors W as lambda here. And those vectors, they turn out to have the following formula, basically, like they have this coefficient which you see here. And you can easily calculate the norm. So the norm turns out to be equal to this number. And so what's important here, we should keep in mind that this set of audible cells sub D appears here. On the other hand, it's a key fact, basically, for this realization from combinatorics that actually for any Young diagram, the following relation holds. And you kind of can compare and see that the only difference is then we are missing some of the audible cells here, basically. And because of this, you can easily realize that actually for some of the Young diagrams, this norm is already 1, meaning that already in those irreducible representations, the measurement is actually projective automatically. But for some of them, it's actually not 1. And it will not be projective measurement, basically, right? Because there's not like norm 1, not normalized states. But you kind of see from here automatically what you are missing. And this kind of gives you an intuition what you need to add, how you should enlarge Hilbert space so that to restore the norm 1 condition here. And okay, so this is the part where I ask you to believe me. So this is an example of a so-called Bratelli diagram. And this Bratelli diagram serves the purpose of actually labeling the Gelfand-Setlin basis. So the Gelfand-Setlin basis is basically is a set of paths in this diagram. That's how you should think about it. And the kind of the last vertex is an irrep of the corresponding algebra. Yeah, in this case, this is an algebra of partially transposed permutations 5, 1. So there are like six qubits, and yeah, the last is partially transposed. And yeah, just an example of this idea which I just described. You just add carefully chosen vertices, and yeah, with a rule which you can find in our paper. And it turns out that on this enlarged Hilbert space, because now Hilbert space has more paths, you can actually construct projective measurement. Actually, how much time do I have? Oh, yes, yeah, thank you. So, yes, so basically, now I explained how we can realize an IMARC dilation of this specific effect operator, which corresponds to the nth outcome. And now it's kind of what we end up with is a now IMARC dilated projective measurement pi. And this pi has this form, yeah, where this pi n is a IMARC dilation of this en effect. And we have and unitaries which you see here, this uk and w tilde, actually easy to implement unitaries. And in fact, this uk, for example, is just a cyclic shift to the power k. And now, if you ask a question how to actually go and implement this projective measurement, well, the answer is kind of easy. So what you want to do, you want to construct this unitary V and do basically a phase estimation on it. So this will implement a projective measurement with those projectors pi. And how you construct such a unitary V, which is here? Well, you use those efficiently implementable unitaries U and W to go into the right subspace and apply the right phase and go back, right? You do it for each one. And then implementation of the power of V is trivial because you just put like, yeah, you just phase, you put this power in this phase over here. Yeah, and then this phase estimation circuit basically implements this projective measurement for you. And yeah, this is basically the idea how you do it. So the total resultant circuit for standard PGM will look something like this. So what you see here on the left, we start with n+1 qubits. So this A1, AN are ports, and this state psi is the state which Alice wants to teleport. And then what you need to do, you need to go to mixture basis. You need to apply this mixture transform, which we described in our previous paper. And then, yeah, you kind of do this unitaries UKW like in this picture, but this is adapted to this specific kind of context. Yeah, and you see you do it essentially linear in n number of times here. And yeah, the circuit you see here is actually in standard encoding, but there is, oh, sorry, yeah. Before I describe the another encoding, I should show you how then we can implement other POVMs. So this was a standard PGM, which was for optimal probabilistic protocol. Now, if you want to do EPR, probabilistic PBT, then what you need to do, you just need to add 1 qubit, literally 1 qubit over here, and do some easy to implement rotation, additional rotation here. On the other hand, if you want to do deterministic PBT, then you kind of add n-dimensional system over here, and you do generalized Pauli here, controlled generalized Pauli. And yeah, if you want to do a generic PBT with this parameterized by this G matrix, you kind of combine those two. And yeah, this is basically the circuit for implementing any kind of conceivable measurement in PBT, which respects the symmetries of this problem. And yeah, as I said, this is an encoding. In the Yamanouchi encoding, what happens is that you have more efficient kind of storability here, but the cost of it is that now the gates somehow are more non-local, and because of this, you cannot kind of optimize the circuit, and because of this, the depth becomes worse in this case, but the additional qubit count is better here. So, and as a final comment, what we also look at, we look at the problem of actually preparing the optimal states. And we find that actually implementing the optimal state for PBT, probabilistic PBT, is efficient. And you can use the circuit described here. And those F gates, which you see here, are, yeah, they depend on this optimal state. And it turns out that these gates are actually easy to implement. And yeah, so this kind of calculation in the beginning happens in this Gelf-unsettling basis. And then you do this Min-Hsiu transform, which brings it back to the standard kind of QUDIT basis on Alice and Bob sides. And then Alice and Bob can use this resource. But unfortunately, the description of the optimal state for DPBT is pretty much still an open problem. And we are not sure that actually it has efficient circuits. So, and so this is basically an open problem for you. It would be very interesting to understand if the similar approach can be used for preparing an optimal state for DPBT. Yeah, and with that, I want to credit all those people for very nice discussions we had. And I would like to thank you for your attention.
Thanks for a very nice talk. So I'm interested in how to, about the state preparation thing. So like for the DCOS2 case, we know the closed formula for optimal resource state, right? In this case, do you know the efficient implementation?
Yes, for PPBT.
Mm-hmm.
Yes,
no, DPBT.
No. Yeah, that's basically the question. That so those gates which you see here, so those gates, right? They kind of act in this Gelf-unsettling basis, and the entries of those unitaries, they depend on basically amplitudes of the resource state. And the resource states for PPBT was understood analytically, and it has very nice formulas. And then you kind of, after some math, you see that in this F gates, you have some ratios of amplitudes. And those ratios turn out to be very easy to calculate. So yeah, you can imagine that you have some kind of additional ancillary register kind of hidden in the box where you do some kind of classical computation. And this computation is very easy. And that gives rise to efficient quantum circuit in the end for the full state preparation. Unfortunately, for DPBT, we don't know any exact formulas for those amplitudes of optimal states. We only have, we kind of know that there exists optimization problem, which is quite non-trivial, and you kind of need to solve it numerically, and this will spit out some numbers for you. So we don't really know if the ratios of those amplitudes are efficiently calculable, something like this.
So can I understand that if you can solve that coefficient analytically, then you can straightforwardly reconstruct the efficient implementation, or is it depend on the specific property of the coefficient?
Yeah, so basically, let me state it as precisely as I can. So what you need for that to be efficient, you need to have certain ratios of those amplitudes to be efficiently calculable classically.
Okay, thanks.
Hey, you mentioned in the beginning the link to non-local computation, right? So I was wondering whether like this line of work would ever give you like more efficient attacks for example, for position-based cryptography or stuff?
Yeah, so I'm not sure about attacks, but so here, what this does give you, so there was a paper, quite recent paper by Alex May, where he actually used pervasive teleportation to prove not the upper bounds, but the lower bounds, actually, for the amount of entanglement. And the complexity of doing this enters basically here. So using our result, it immediately translates into better lower bound. So basically before the amount, like the lower bound was like double log, and now it's basically log of the complexity. Yeah, so it's kind of automatically exponentially improves because we brought the dependence in N. We exponentially improved dependence on N here. Yeah, but as another, actually, yeah, it's good that you asked because an open direction basically here would be to actually explore further if you can bring the complexity, kind of, can we make it actually into log, polylog n, or maybe polylog d? Okay, doing both might be too good to be true, but separately, maybe yes. So that would be another direction to explore here.
Hi everyone, I'm Min-Hsiu, an assistant professor.
This.
Hi, everyone. I'm Min-Hsiu, an assistant professor in computer science department.
Thank you. Can everyone hear me clearly? Okay. So today I'm going to talk about limits of noisy metrology with restricted quantum control. Okay, so as a basic introduction to quantum metrology is the science of estimation in quantum systems. And here are just a few examples. The first one is optical interferometry. You have an unknown parameter in your quantum system, which is the difference between two optical paths. And then you try to use interferometry to estimate the phase difference between two optical paths. And then this is a question in quantum metrology. And then the second example is atomic clock, where you the unknown parameter is the laser frequency, and then you try to use a bunch of qubits or atoms to sense how large is the laser frequency here, which is an application in atomic clock. And then this is also falls in the range of quantum metrology. And finally, you can use, for example, like nitrogen vacancy centers as qubits to detect like magnetic fields or electronic fields, which can be unknown in the quantum system. And then this also is an example of quantum metrology. So I'm not going to talk about any specific experimental platform. Instead, I'm going to focus on a abstract model behind this experiment, which is the following. So basically, in all quantum metrology, or most quantum metrology experiments, you always have some kind of quantum signal you want to detect in your quantum system. And then you also have some level of quantum noise in the system. So this is something that inherently exists in your quantum system, and then you cannot have control over that. Instead, what you can control is how to generate an input state, which is the state preparation part, and then what kind of measurement you perform in your quantum system. And then finally, what kind of quantum control you apply during the evolution of the system. So basically, you try to control these three parts in order to maximize the sensitivity with respect to your quantum signal. So for a more information theoretical language, you can call this a quantum channel estimation. So basically, I would assume you have a quantum channel, which is an arbitrary CP-TP map that depends on some unknown parameter omega. And then I also, for simplicity, I assume omega is like around 0. So it's basically a real number, and I assume like the true value is around 0. And then here is something called sequential strategy, which is basically one type of quantum control you can apply to sense this unknown parameter. In this case, you are allowed to have an arbitrary input state and then an arbitrary quantum control you can apply it during the evolution, and finally a quantum measurement. So this is called sequential strategy because here the quantum channel applies on a single probe multiple times instead of this strategy where you basically apply the quantum channel on multiple probes, in parallel multiple times. So this is not as general as a sequential strategy, but it is also widely applied in quantum metrology. And one question to answer is with these strategies and with the number of channels sufficiently large, what's the scaling of the estimation error with respect to the number of channels? So there are two types of limit people usually consider. The first one is Heisenberg limit. So it describes the situation where the estimation error is proportional to 1/n. And then the second limit is standard quantum limit. It describes the situation where the estimation error is 1/√n. So they are actually the only two types of limit that is allowed if you optimize over all the sequential strategy or parallel strategy. So basically you choose the optimal sequential strategy for the specific quantum channel, and then you get either one of this scaling. And basically you can achieve the standard quantum limit by just using product state. And you don't need any entanglement in order to achieve the standard quantum limit. But in order to achieve the Heisenberg limit, you need to use some kind of entangled state or maybe the coherent evolution of the quantum system. So, and then there's another equivalent way to say these two type of limit, which is using the language of quantum fission information. So basically, the estimation error can be related to the concept called quantum fission information through this Parmel bound. So it basically states that the estimation error can be as small as 1 over square root of QFT if you choose the suitable estimator to detect omega. So if the fission information is n squared, you achieve the Heisenberg limit, and then if the fission information is linear, you achieve the standard quantum limit. So here's a bit more detail on how exactly do you distinguish between these two cases. And then it basically depends on one specific criterion that you can easily verify for a specific quantum channel. It's called Hamiltonian not in crossband condition. So basically, given a quantum channel, you can calculate the Hamiltonian of this quantum channel, which is defined using this formula over here. So you don't need to understand like why it has this expression, but basically you can calculate it, and it is a Hermitian operator. And then the other thing is called the crossband or the span of noise. So it's basically a span of linear operators, and then it is spanned by the operator ki dagger kj. So if the Hamiltonian is not inside the crossband, you can build up some quantum error correction protocol that allows you to achieve the Heisenberg limit using the sequential or the parallel strategy. But on the other hand, if the Hamiltonian is inside the crossband, you cannot achieve that. Okay, so I'm not going to go to the details about that criterion, but I'm going to stick with this simple example throughout this talk. So in this example, I just have one qubit, and then the Hamiltonian, I would assume, is the Pauli Z operator, which is basically the, then you can consider the channel as a rotation of the Pauli Z operator, and the strength of that rotation or the angle of that rotation is the omega, which is the unknown parameter you want to estimate. And then if the error is a Pauli Z operator, you can see that the condition is actually not satisfied. So basically the Hamiltonian is inside the crossband, so the Heisenberg limit is not achievable. But on the other hand, if the error is bit flip noise, that means the Hamiltonian is not inside the crossband, and actually you can use the error correction to recover this Heisenberg limit. So now I'm going to go to a bit detail in terms of how to achieve the Heisenberg limit or standard quantum limit with in this example. So in the first situation, I'm going to consider you have no noise at all. In that case, you don't need any type of quantum control. You just apply the same channel on the qubit multiple times. And in the situation where you start with a plus state, you will have a phase difference, which is omega n, and it is proportional to n between 0 and 1. In that case, you naturally achieve the Heisenberg limit by performing a measurement on the output quantum state. And you can also achieve that using parallel strategy, which in which case you need to use a GHZ state as an input. So it generates, again, a phase difference that is proportional to n, which allows you to achieve the Heisenberg limit. So these are the two situations where you have no noise at all. And what happens if there's bit flip noise? So recall that if we have bit flip noise and Pauli Z Hamiltonian, we can actually recover the Heisenberg limit. So how do we do that? In fact, people just use something called a 2-qubit repetition code. Why is it 2-qubit? Because we assume we have one noiseless ancilla, which is this one over here. So this qubit is definitely correct. So basically, we just need to correct the first qubit based on the information from the second qubit. We just align the sign of these two qubits, and then it actually corrects any bit flip noise. And in addition, it does not destroy the Pauli Z Hamiltonian, although we might have a constant factor difference between the optimal, like in the noiseless cases. But actually, we can asymptotically we can always recover the Heisenberg limit using the error correction in this way. And similarly, if we consider the parallel strategy, again, we can use the GHZ state. The reason is that it is basically a like a logical plus state with the repetition code. So again, you just use like majority voting to decode the state, and then it would give you back the Hamiltonian scaling. as if there's no noise. Okay, so these are all like the situation where you can recover the Heisenberg limit. However, as I said, if a noise is the same as the Hamiltonian, which means your noise is dephasing and the Hamiltonian is also Z, in that case, you can only achieve the standard quantum limit. And in order to do so, you just need to use, for example, like a product state. Sorry, there's no L there. Okay, so this is the example from the previous literature. And one thing I'd like to point out is that although we can recover the Heisenberg limit when there's noise, the protocol is quite complicated. So for example, if we want to use the sequential strategy, then we need to have noiseless ancilla, which is quite expensive in practice. And we also need to perform CPTP channels during the evolution, or at least some kind of mid-circuit measurement, which can be quite noisy in practice. And then if we want to resort to the parallel strategy, that means we need to scale up the system to a very large system size. And moreover, we need to have like long range entanglement in both the state preparation part and the measurement part, which can also be quite expensive in experiments. So this motivated us to study the case where we only have restricted type of quantum control. So the first type of control I consider, which is the most restrictive case in this talk, is the ancilla-free sequential strategy with only unital control. So basically, I assume no noiseless ancilla, and I also assume you can only perform unitary control during the evolution. And then there's another slightly more general protocol where I allow CPTP controls during the evolution, but then I allow no noiseless ancilla, as in the sequential strategy. And finally, there's a different, slightly more general protocol compared to the first one, which is the situation where you can have a constant size of ancilla, but then only unital control during the evolution. So these are the three types of restricted control strategy I consider. And okay, so why is that important? So one important thing is that if you only consider qubit channel or qubit quantum noise, then with these three different types of strategy, you can no longer do any protocol with quantum error correction with this restricted control. So, and this is the first thing. And then the second thing, even the achievement of standard quantum limit becomes non-trivial in this case. The reason is that you can no longer do measurement every step of the evolution, because every step you just do a unital control or CPTP controls. You only do one final measurement in the end. So this makes the situation much more complicated than the previous case. Okay, so now I'm going to discuss what's the metrological limits under this restricted control. And I'm going to focus on qubit channels. So the advantage of qubit channel is that you can easily classify them. So there are actually three classes of qubit channels if you ignore all the parameter dependence thing. So the first type of qubit channel is just unitary channel. You just have one unitary rotation on your qubits. And then the second type, which I call dephasing class channel, means that you can rotate the channel to a dephasing noise. So basically, you can apply a unitary U before the dephasing class channel, before the dephase channel, and then a unitary V after the dephasing channel. And then I call this type of channel dephasing class channel. For example, like bit flip noise is also a dephasing class channel because you can always rotate X to Z. And then finally, there's if the channel does not belong to the first two type of class, it has to be a strictly contractive channel, meaning that it will strictly contract the trace distance between two quantum states. Okay, so here's I'm going to show the result in this table. So basically on the horizontal line, I have different strategy. The first one is the sequential parallel strategy, and then the other three are the restricted type of strategy I consider. And on the first column, I have four type of qubit channel. So again, we have the unitary channel and the strictly contractive channel. But then for the dephasing class channel, I have to divide it into two types because actually we have two situations. The first one is, again, if the noise does not align with the signal, we would have the channel falls into the first class, and then if the noise align with the signal, it falls into the second class. Okay, so then here's the result. On the first column here, we already know that we can use HNKS condition to help us determine the scaling of the quantum Fisher information. So basically, if the channel is dephasing class channel or of the second type, or the strictly contractive channel, we can show that the HNKS condition always fails. So that means the Fisher information is like at most linear in this case. Okay, and then how about the other restricted control strategy? Note that here we show that basically for any noisy quantum channel that is not a unitary channel, the Fisher information is at most like linear, or at least it's not going to be quadratic. It's at most like n to the power of 3/2. So how do we prove that? It's based on some analysis of the quantum Fisher information. And we use something called the channel extension method. I'm not going to go to the detail here, but basically it depends on analysis of quantum Fisher information. So this, and also we can prove that for the dephasing class channel of the first type. Okay, so basically for the dephasing class channel of first type, which is the second line here, we also find a linear lower bound on the Fisher information, where we design some unitary control sequence that allows us to achieve the standard quantum limit without doing repeated quantum measurements throughout the evolution. So we just need to perform a unitary every time step and then one measurement in the end. Okay, and then the other thing about the Fisher information is that the Fisher information is at most a constant for dephasing class channel of the second type with the first type of restricted strategy. And in order to prove that, we use some calculation with the block sphere representation. And finally, in order to prove the constant Fisher information upper bound for strictly contractive channel, we just need to use the relation between Fisher information and Brest distance. And then we use some contraction coefficient with respect to the quantum Fisher information. So basically, to summarize, if we are allowed to perform sequential strategy or parallel strategy, there's a clear dichotomous behavior between the channel that satisfies the HNKS condition and does not satisfy the HNKS condition. And this is our new provable separation. The first one is a separation between unitary channel and all the noisy quantum channel, where we show that for all noisy quantum channel, we cannot achieve the Heisenberg limit anymore. And then the other separation is a separation between dephasing class channel of the first type and the other noisy quantum channel. So basically, if it's a dephasing class channel of the first type, we can achieve the standard quantum limit, but then for the other part, we cannot. It's just the constant quantum Fisher information. So, but still, there are many open questions. For example, we don't know the distinction between CPTB controls and unital controls, and then we don't know the distinction between the dephasing class channel of the second type and the strictly contractive channel. So finally, I'm just going to talk a little bit about how the unitary control sequence actually works. So basically, if we have bit-driven noise and the Pauli-Z Hamiltonian, we can actually achieve the standard quantum limit by only performing unitary control. And this is how it looks like. So it's actually a control that is uniform throughout the evolution. It's going to be a rotation around the axis, and then the angle depends on n, which is the time steps. And then in the end, you can have a derivative of the state that is proportional to the square root of n. And it implies that you can achieve the standard quantum limit. So here's like a numerical simulation. You can see that if you are allowed to use quantum error correction, you can definitely recover the Heisenberg limit. But if you only use unitary control, you can actually recover a very good linear scaling of the quantum Fisher information. And then this is even like more performs better in terms of the exact value of the quantum Fisher information, because the Fisher information is actually larger than the situation where you perform no control but only repeated measurement. So, okay, so to summarize, I demonstrate that the structure of noise and the signal determines the estimation precision limits in metrology. And also, I show that the Heisenberg limit is no longer achievable on the qubit noise, but the achievability of the standard quantum limit has a new dichotomous behavior. And some future direction include generalization to qubit system, and also to include measurement and feed-forward controls during the evolution. And finally, how to calculate the exact value of the QFR instead of just the scaling of it is an open problem. So yeah, thank you for listening.
Hi, thank you for a very nice talk. And your main result, that table looks very nice. Just one thing I'm quite curious about is what is the mathematical technique you use to get that table and solve this question? If complicated, maybe just some ideas if you could give.
Yeah, so basically I need like 3 types of techniques as shown here. And I think maybe the most important one is the first line, the channel extension method. Basically, it gives you a simple way to calculate the quantum fission information of a quantum channel, because in general it's pretty complicated. But if you fictitiously allow an ancillary system as an input of a quantum channel, then it gives you expression of quantum fission information which is easier to compute. And you can express that using a semi-definite program. And then basically by using this channel extension method, you can bound the quantum fission information, put bounds on quantum fission information. And then, for example, you can show that it's at most linear if you use like unital control. So that's some idea. And maybe the last line here, you need to calculate the difference between the fission information of an input state and output state. And then you can call that the contraction coefficient. And then that might also be useful, like improving like the last line here. Yeah.
I see. So it means with these techniques, you can have those conditions about which is the give the condition to the control in this process.
Yeah. So basically, like these kind of techniques, you can show that it works for this type of controls. So that's why it works, like to show this scaling.
Okay. Thanks. Yeah.
Thanks. Thanks for the very nice talk. So I wonder if this unachievable Heisenberg limit is related to the lack of decoherence-free subspace.
Yeah. So so if you have a decoherence-free subspace, of course you can achieve the Heisenberg limit. And then if you don't have decoherence-free subspace, like in principle, you can use like error correction to do that. But then since with this protocol, you cannot do error correction, then you cannot achieve the Heisenberg. So it might be related, but then it's not like a necessary and sufficient condition. So I don't know the relation between.
Thanks.
All right, very nice. Can I just ask for the dephasing class where the H and KS holds, so between the sequential ancilla free and the sequential is just taking away the ancilla? That's the only thing you're doing?
So you mean like the first and the second column? Yeah, so I'm taking away the ancilla, and then I also assume you can only do like unitary control.
Oh, so the first column is measurements as well? Yeah,
so basically because you have like, in the first column, you have ancilla, so you can always defer the measurement to the end. So then it effectively means that you can do mid-circuit measurement. So yeah, but then in the restrictive control strategy, I don't allow sufficient amount of ancilla. That's why you cannot do measurements many times as you want. Yeah.
Thanks.
Thank you for your talk. I had a question about, for extending your work, what class of measurements would you perform in the systems?
So it's actually like arbitrary POVM you can perform on the output state. Yeah. Yeah. So I have no restriction on the measurement. Yeah.
And so once you get a measurement, you get like some measurement output, and then you would condition like the dynamics over time on like what measurement outputs would you get, or you think like more you do more measurement at the
you
end?
mean like mid-circuit measurement?
Yeah.
No, I don't allow that because like here I only allow like a constant size ancilla. So that means I can only do mid-circuit measurement like constant time. But then the system is like infinitely long. So then you cannot do mid-circuit measurement every time step. So,
Okay.
so I don't allow that. Yeah.
Thank you for a very interesting talk. This may be a very abstract question, but I thought that this situation in ancilla-free sequential strategy is quite similar to like quantum error mitigation. And yeah, I just want to know that. So, is there any connection between your result and error mitigation?
Yeah. So there might be some connection, but currently I don't see like it directly applies to error mitigation because like right now the protocol I consider has like the unknown parameter in the quantum channel instead of like in the initial input state. So if it's like in the initial state, then maybe you can consider like how the phase information change after the evolution. But then since it's in like every time you put some new signal in the sequence, so there's some distinction, but then maybe some connection. I don't know. Yeah.
Do you have any closed form expressions for the control signals?
Yeah. So since I only consider like single cubic case, so it's actually quite simple analytically. So it's just like this type of unitary control. So it's just the rotation that is along the same direction as the signal. So basically it just tuned the angle of the rotation to a specific direction.
So this is for the dephasing class channels, right?
Yeah.
For contractive channels?
Yeah, for contractive channel, basically, I show that it is at most constant. So yeah, so basically, like any type of sequence, it does not allow you to achieve the.
Oh, I see. Okay. Okay. Thank you.
Hi, everyone. I'm Min-Hsiu, an assistant professor in computer science department at UC Santa Barbara, and also a research scientist at Google Quantum AI team. And I'm grateful for the organizers for me to be able to give a virtual talk today about a work with my amazing students and collaborators, Yulong, Honor Bennett, and Hsieh Samuel Tan. We proposed a new quantum metrology algorithm that uses extremely low depth circuit to learn quantum gate parameters to the highest accuracy today. And we achieved that not with the conventional linear coherent amplifications, but with nonlinear transformation induced by the universal framework of quantum signal processing. And before I delve into the detailed structure of our algorithm, let me first define what do I mean by quantum metrology. The metrology has two parts. The metron come from the Latin word that means measurements, and logi from logo means learning. For quantum metrology, we perform projective or weak measurements and use the measurement results to learn about system parameters such as environmental defects or quantum state or gate values. And there are two very critical goals for quantum metrology. One is we want to be extremely accurate and extremely efficient with regard to the number of measurements, computing resources, and time. And the accuracy is crucial since we are at the pivotal moment of crossing the fault-tolerant threshold. To validate that we crossed the very low fault-tolerant error threshold, say 10 to minus 3 error probability, our algorithm has to function at even lower error rate, for example, 10 to the minus 4 in error. This, to our knowledge, has not been achieved before our work for arbitrary two-level systems. And efficiency is also crucial since maintaining quantum computer requires us to routinely recalibrate the whole device, where quantum metrology is a basic subroutine. So more efficient quantum metrology literally means more time to use the quantum computers for useful computation. So accuracy and efficiency are the main goals for extremely useful quantum metrology algorithm. And we can also characterize or categorize the existing methods according to the efficiency, which is the runtime, and the accuracy, which is the scaling of the accuracy versus depth, as well as the applicability, for example, whether we can learn open system dynamics or not, and whether we are robust against state preparation and measurement error or not. I won't go over every detail in this table, and it's not a complete table, of course. But today, we will focus on the lower right corner, because as we increase our knowledge and control of the system, we're moving essentially from the upper left corner where we have the minimal amount of knowledge of the system model, but we require a lot of resource overhead to learn about the system parameter, to the lower right where we have sufficient amount of parameters and modeling of our device such that we can achieve the highest accuracy and efficiency. And in fact, Google, our team at Google pioneered the method called periodic calibration. It is a multiple parameter generalization of robust phase estimation. And it's the only algorithm, to our knowledge, that achieve Heisenberg limit, polynomial runtime, and can be adapted to learn open system and closed system dynamics, and is spam resilient. However, this method is not good enough yet to achieve this 10 to minus 4 accuracy. And I'll try to explain to you why. And before that, I have to first go over how high level how this algorithm works. So similar to the original robust phase estimation, our multi-parameter periodic calibration also have this type of periodic circuit where if I want to learn this target unitary gate parameter, for example, zeta and phi, I will repeat this gate multiple times, maybe followed by some single qubit operation, and then measure the probability at the end. So this gave me a transition probability from the initial state to the measured phase stream. And by repeating k time, the coherent parameter we want to learn, which wrap around inside this omega parameter, will be amplified at a factor of k. And inverting this expression allows us to achieve the Heisenberg limit, where the variance of our learning algorithm scale inversely quadratically as a function of k. And this seems fine, but most of the prior art do not really care about the optimality of this scaling, which is the coefficient multiplicative factor in front of the scaling. And in fact, robust phase estimation and periodic calibration, they all have of order magnitude 1 in this coefficient. That means if we do want to achieve, say, 10 to minus 4 in standard deviation of our metrology tool, we would need around 10,000 repetitions. This is beyond any existing quantum computer's capability. So another really hard difficulty is that in a lot of devices, including the ones in superconducting qubits, the gate parameters such as this phi in this swap Fsin gate can drift over the course of the repetition inside the same circuit. And because the way we inferred our parameters theta and phi, we require to invert the overall probability at the end of the circuit, which is a function of theta and phi. Any error in phi will trickle down to errors in all the other parameters. as evidenced by our experimental result here, where we measure the swap angle theta as a function of different reputations, and we look at its standard deviation. We notice there's a huge spread in its performance accuracy due to the drift effect in this prior art method. So to address this main issue and to really achieve another level of accuracy not ever achieved before, we propose a new way to learn these gate parameters. And instead of linear amplification, we use nonlinear transformation to separate the time-dependent term from the time constant term, while at the same time to really achieve the optimal inference by having this optimal coefficient in front of the Heisenberg limit that's permitted by the Karmarov bound. And we show that our algorithm turned out to be near optimal even respect to the quantum circuit measurement optimization that is given by the quantum Karmarov bound. So now, in order to really understand our method, I'll give you a high-level introduction of quantum signal processing. The classical traditional signal processing really bear the exact same flavor, which is if I give you a signal and you want to transform to other type of signal, from audio signal to electromagnetic wave, and then back to audio signal. Or we can transform a noisy looking signal through Fourier transform to extremely structured signal. And quantum signal processing, the only difference really is the input signal, that it's generated by quantum dynamics. For example, in the simpler case, correspond to a single qubit rotation. And the signal is defined by the probability of the transition from 0 to 1 after I apply the quantum, this single qubit rotation as a function of the rotation angle. And so if you only have one rotation, this type of signal is very simple. It's just a cosine or sine function. However, if I have multiple rotations, and if I can choose the rotation axis, I can engineer very sophisticated shape. For example, this one looks like a flat top type of shape. And this groundbreaking work by Guanhao, Ted, and Ike, they show that, in fact, it is universal for us to realize any degree in trigonometric polynomial functions with n rotations. For example, we can approximate a neural network activation function. And the reason how it works, we can visualize the underlying dynamics by, for example, rewriting this single qubit rotation into purely Z rotation and purely X rotation. Then the only parameters that we're changing to program the transformation are the Z rotations. So in that sense, it's almost like a electromagnetic field where we're programming the electric field with a fixed magnetic field to transform quantum information. And of course, this analogy is only on the intuitive level, not on a very rigorous level. Rigorously, we can systematically generalize the single qubit transformation where we're performing a polynomial function onto the original scalar element of a 2x2 matrix into a polynomial transform on the matrix block diagonal, the upper left block of the block encoded matrix. So what we can do with this capability is essentially every single quantum algorithm then can be realized. For example, quantum simulation algorithm require us to implement exponentiation of a target Hamiltonian function. And we can realize the same task by polynomial approximation of this exponentiation function. In fact, quantum signal processing and qubitization-based simulation is one of the most optimal in regard to query complexity for among all the existing quantum simulation algorithms. But it is not yet really optimal or efficient enough for deployment in real system because the error rate for simulation needs to be around chemistry accuracy 10 to minus 10, which is definitely require fault tolerance. So we're asking the question whether we can harness this universal transformation power to design new type of quantum metrology algorithm. And so that leads me to our quantum metrology algorithm based on QSP. And we start by defining the problem where we want to learn an arbitrary 2x2 unitary. And this unitary, learning this unitary allow us to learn most of the 2-qubit gates available. For example, in superconducting system, the 2-qubit gate have this type of particle conserving structure that is block diagonal into a 2x2 matrix. So we only need to learn 2-level unitary at a time. And similar for ion traps, more Sorensen gate. So the problem is if you give me this type of U gate or 2-level gate, an arbitrary single qubit gate and projective measurement, our task is to infer all the parameters in this gate. And to use QSP, we can look a little bit harder on the type of U-gate parameterization. It very similar to the qubitization we discussed earlier in QSP. And so to leverage this structure, we have additional design our circuit, which look very similar to the original periodic calibration circuit, where we have repetition of the target gate followed by Z rotation. But the difference are in the initial state and post-processing. So the initial state, we use a Bell state defined by support with a different phase onto the 1, 0 and 0, 1 state, such that everything we're looking at is inside in this 2x2 unitary. And based on different bases, we get 2 different measurement probability of measuring 1, 0 at the very end. And after the using the same analytic analysis of QSP, we can analyze what's the outcome if I combine this 2 probability measurement. We can have this really neat expression where the Fourier transform of this probability will give me a very simple function of the parameter I like to learn, where the amplitude of this Fourier transform give me the theta angle, and the phase give me the phi angle. In this way, we completely diagonalize the 2 interdependent parameters theta from phi. So that drift in 1 for the phi does not really affect theta that much. But because of the requirement of this Fourier transform, that means I need to apply this quantum circuit at different omega, where omega is the corresponding frequency of the Fourier transform. So now our experiment take D different circuit, and the depth of the circuit is also depth D. And then we can perform measurement and deterministic post-processing. In this way, we can replace the requirement of a black box optimization that is needed in the prior art. Moreover, we show that we have a very simple estimator for the parameter we would like to learn, the theta and the phi, and our estimator is in fact maximum likelihood estimator, and it's optimal in regard to its variance compared to classical Cramer-Rao bound. So this means our estimator is optimal in regard to the post-processing for the given measurement circuit. And here we show the comparison between the Cramer-Rao bound, which is a solid line, and our performance, which is on top of the dashed colored line. And the dashed black line is fitting to the scaling to show you how does it scale. And you can notice that the parameter phi scale 1 over d to the power 4 at the short depths. This on the surface look like as if it's faster than Heisenberg limit because we only have a depth d circuit. But if you read our paper, you'll notice this does not violate the asymptotic Heisenberg limit. As you increase the d sufficiently long, you can, the scaling of phi will converge to the normal Heisenberg limit. But another important thing is we are not only optimal with respect to Cramer-Rao bound, we are also only a factor within a factor away from the optimal circuit design for the quantum Cramer-Rao bound. And this factor 2 is kind of unavoidable if we want to achieve a deterministic estimator. And compared to the prior art of the periodic calibration, which is represented by the dotted line, which is its own performance compared to its own Cramér bound, there are several magnitudes off from their own Cramér bound. And their Cramér bound is also a couple magnitudes worse than our QSP estimation and performance. And lastly, our method is also robust against open system dynamics that is describable by a depolarizing error. We showed that the overall effect of a depolarizing error of the strings alpha only rescale our estimation of theta. So we provide a way to directly estimate the depolarizing strings and use that estimation to compensate its effect in our inference for theta. So on the right-hand side, we show you its performance in simulation under the depolarizing noise, where it converges pretty fast under both depolarizing noise and time-dependent drift in phi, as we expect such decomposition should offer. And lastly, we have tested it on the real device with 17 pairs of superconducting qubits, where we are learning the 2-qubit FSIM swap angles using the quantum signal processing estimation. And we plot the result here, where the x-axis are the result for our method, and each dot is a different pairs of qubits. And the y-axis is the result from the prior art. And as you can see in the prior art, the variance of the estimation on theta is spread all over the place, maybe largely due to the different drift of phi qubit to qubit. But our method is concentrated around 10 to the minus 3 to 10 to the minus 4 in the standard deviation of theta. Moreover, the circuit depth that we need for our method is reduced from around 100 to 5 to 10 depth circuit. So in this way, we are achieving both magnitudes of improvement in accuracy and in efficiency. So to summarize, we can go beyond the traditional way of linear amplification for learning quantum gate parameters if we leverage the universality of quantum signal processing transformation. And we have built indeed a quantum signal processing estimation to learn quantum gate parameters, and it's to our knowledge the first time to be achieving this optimal efficiency in real experiment, and very near optimal in regard to our measurement circuit design. And we overall offer around 2 magnitudes improvement over the prior art in regard to the Heisenberg scaling efficiency that allow us to reduce the required circuit depths to 100 or to 1,000 down to less than depth 10 circuit. And given that quantum signal processing can be used to realize any universal quantum computing task, so instead of waiting for a fault-tolerant quantum computer to arrive, which already have close to 0 errors, can we design error correction with real-time feedback using quantum signal processing that integrate with our quantum metrology algorithm? Indeed, in a recent work of ours, we show that quantum signal processing have already a very nice structure that we can use for feedback or feed forward. In this way, we can try to avoid this type of millions of qubit requirement in regard to the resource that's needed for real world impact. Lastly, I like to thank you and thank my collaborators. Yulong Dong, who is previously in UC Berkeley, is currently looking for quantum jobs. Feel free to check out his homepage and all the students involved here. My group at UCSB have also positions open for postdoc graduate researchers. So feel free to email me if you're interested to join us to do quantum research and to do surfing. Thank you.
Yes. Yes. So thank you very much. So I'm going to present our joint work on joint work together with Harry Buhrman, Verduyn Lunel, and Jordi Weggemans on permutation tests for quantum state identity problem. So actually, Jordi is also here at the conference, but I believe he is now might be at the session A. So please don't hesitate to ask him questions about this work during the. Okay, so yeah, so the basic setup for this work, kind of, it's all motivated from the swap test. So the swap test is a very classical primitive in quantum computing, which basically answers the question how we can compare two states. So imagine that we are given two quantum states, Psi1 and Psi2, and we are promised that they're either orthogonal or they're identical. Then we know for a very long time from those fundamental works that if the input of two, if you have an input with two identical states, then the measurement probability of an answer that they're equal is 1. However, if they're orthogonal, then we only measure this with 1/2 probability. And the natural question to ask is how actually optimal this test is for this particular problem. And it was proven that it's actually an optimal test if we impose a perfect completeness requirement in this paper. And what does it mean, perfect completeness requirement? So perfect completeness means that if we are promised, and so if we are given an input with two equal states, then we are required to answer with 100% probability correctly. So yes. Actually, sorry, I'm a bit confused. Maybe I should start again. Because I assume people were, yeah, maybe we started too early. Okay. Yeah, so basically, the basic question is to ask if we can generalize the swap test for arbitrary number of input states. So, and this is the question we want to study in all the details in this work. But of course, there was some work done before us, and yeah, and before I describe the results of the previous work, let me introduce some terminology. So I'm going to distinguish two types of errors, how it's usually done in statistics. So type 1 error, or sometimes called false positive error, or sometimes called soundness error, is basically when we given the positive case, we answer incorrectly. And the positive case for our state identity problem will be that all states are assumed to be identical. This is the positive case. And the type 2 error, or called false negative, or called completeness error, is basically an error when we are given the negative case and then we answer incorrectly. So the negative case for this task will be that some of the states are actually orthogonal. And then the figure of merit for us will be actually the average success probability. So given some prior that we are given some either a positive case or a negative case, we want to calculate the success probability, like the average success probability for our protocol. Yes, and we can also consider even more requirement on the input in principle, right? So we can consider some more promise on the input, and we can consider the average success probabilities with more prior, so to say, on the input. In principle, we can also optimize such probabilities. Okay, so given this terminology, I'm ready to state precisely the problem we are formulating in this work. So the input for our problem is n unknown qubit states, psi1 up to psi n. And so we are promised that they are pairwise orthogonal or identical. Yeah, so this is like the first promise is that they're all identical, like the first case, which we want to distinguish from the second case. And the second case is a bit more tricky, so we want to be very precise what we mean by non-identicalness. So in one case, we assume that what we know is that only there exists some indices for which the states are pairwise orthogonal. This is, so to say, maybe the most agnostic way to formulate this. Another case is when we are given some partition of the number n, such that the input state, like the total input state, is of this tensor product form. Yeah, of the tensor product form like here. So we kind of don't know the basis, so we assume that we have some random unitary. But we know that among those n states, there are mu1 states which kind of equivalent to ket1 and mu2 states to ket2 and so on and so forth, right? So we kind of know the composition of our input. And here we crucially, so the tilde here means that we also don't assume any knowledge kind of on the permutation, right? So principles that can be given to us in the random order. And finally, maybe the most strongest kind of assumption, which we may have for this work, is that we are given this input state in the tensor product form, but we don't know the basis, but we kind of know the order at which they are given to us, right? And so in all of those three cases, we always assume that the case one happens with probability p. And so this is like some kind of prior probability which we can also adjust. And the task would be to find the protocol, right, which given those assumptions return equal if we are given the case one and unequal in the case two as often as possible. Okay. And so this brings me back to an earlier work, which basically influenced the most our current work. So this paper by Kada, Nishimura, and Yamakami from 2008. So what they basically proved, they generalized the optimality result for the swap test. So they showed that a generalization of a swap test when we have now n qubit states actually is also optimal on the perfect completeness requirement. Right? So again, the perfect completeness requirement here means that if we're on the case when all those states are the same, our protocol should answer with 100% probability correctly. And so generalization of the swap test is kind of very logical here. So it's called permutation test, meaning that so in the swap test, you remember we had like a qubit, right? And we applied like a controlled swap operation. And here it's basically the same. Now we have an ancillary register, but now we apply the control over all possible permutations over n systems, right? So the n factorial such permutations, and in principle, we would need the n factorial dimensional ancillary register here, meaning that we would need to use a QFT on n log n qubits here. Okay, and so this work not only proved that the permutation test is optimal under perfect completeness requirements, they also considered a different kind of tests, namely one very concrete example is a cyclic test or circle test, where instead of all permutations, you apply only cyclic permutations. And what they also managed to prove is that it's actually optimal, again, under perfect completeness requirement, but only for prime n. And it achieves 1/n error for arbitrary n. And so the reason to consider such a test is that now like the circuit is much simpler, and because we only have n permutations instead of n factorial permutations. Yeah, and so we need to use a quantum Fourier transform only on log n qubits for in the ancillary register. There was another paper, quite a recent one, which proposed another type of test, which is interesting in the sense that it doesn't use any quantum Fourier transform. It only combines in smaller swap tests in such a circuit. You can see here. So you assume that you have some kind of selected state, and then in principle all the other states can be the same, and they proved optimality in this rather very restrictive condition that it's actually optimal for arbitrary n, only in this input case. And so this kind of naturally motivates the problem following this work 2008. They already raised this question there. So what happens if one relaxes the perfect completeness requirement? Can we still prove some kind of optimality of a permutation test, or maybe we need to use some other test? The first question. The second question, can one find some simpler approximations, some other tests which would be easier to implement and have lower complexity to implement? Yeah, for example, like in this paper in 2018, which uses only subroutines of swap tests, smaller swap tests. Another question is actually to understand maybe broadly what is the underlying mathematical structure that allows to achieve near optimal performance for this simpler test, which is not a permutation test type. And finally, what we can say actually about the performance of the test beyond worst case inputs, meaning that if you assume some additional assumptions on the input, maybe we know some, as I showed earlier, we have this composition mu. If we know mu, can we actually say something about this average success probability of our tests? Okay, so these are the questions which motivated our work. And okay, the main takeaway maybe for you is actually everything is fine. Permutation test is optimal without perfect completeness requirement. Well, there is a fine print that into slightly modifying permutation test is, if we don't assume a perfect completeness requirement, there's a regime for the prior where actually an optimal thing would be to do the most stupid thing you can do, just output the same for each time. In the other case, it will be permutation test. And also, kind of the second takeaway from our work is that we use a lot representation theory and group theory to show a very general formula for performances of more general kind of tests, which is based on subgroups of symmetrical. Okay, so this is like the main takeaway, and now I can describe in more detail our results. So what I just said in words, there exists some optimal probability P star such that, so this is this prior probability, such that, if we are above this probability, then actually permutation test is optimal for if you want to maximize average success probability. And it still achieves perfect completeness, and it has a soundness error, or as a soundness probability, which is given by this formula, 1 minus 1 over the multinomial coefficient. And this probability has a very simple, this P star probability has a very simple form. And on the other hand, if we kind of have lower prior than the P star, then actually the optimal thing to do is just always output unequal, which is kind of maybe not so surprising. But now, we have this rigorously proven. And in principle, we can compute an average case performance over any input distribution. Okay, what we can conclude from this result? So the first one is actually that in this sequence of these three different quantum state identity problems, which I described in the beginning. The last one had a lot of knowledge in a way about the order of the systems. And it turns out that actually the order doesn't really allow to achieve higher success probability. If you know this order, it doesn't really help you. The second thing we learned is that relaxing one-sided error requirement doesn't really increase the average success probability. And yeah, the last thing is that the permutation test actually perform much better on most of the inputs than those worst case instances. And those worst case instances have this 1/n soundness error. But if you know this mu decomposition, then in principle you can improve this much. You can improve this a lot. Yes, and so yeah. So this is the main conclusions from our theorem. So how do we prove this? Okay, so this is like the sketch. So what we need to do? As I said in the beginning, we assume our input has the form like u to the tensor n times times some pure state written in a standard basis according to the composition mu. And what we need to do, we need to average with respect to Haar measure such a choice of the state. And we will formulate the problem of finding the optimal measurement as an SDP, optimization. And so this will be a primal problem for us. The permutation test itself actually is just one example to this optimization problem. It's a feasible solution to this primal problem with some objective value f, which we compute. And then we need to look at the dual problem. So it's just like a standard trick. We will look at the dual problem. We'll make some educated guess for the dual. And we will show that this dual feasible guess will have some objective value f star. So yeah, for that we would need to rely heavily on representation theory on Verduyn calculus, but it's not so difficult calculation in the end. And what we will see that actually those two values are equal. So the weak duality will imply actually that the permutation test is optimal for the Haar random choice. Well, and so there is very last tricky thing is that we need to show actually that the Haar measure is in fact the hardest measure of all possible inputs. And yeah, so we also need to do this step. And finally, this proves that we prove our theorem kind of agnostically to the underlying measure. And so, as I said before, we want to also to consider other tests, which do not use all the permutations of the symmetric group, or only to focus on some subgroup. And in principle, we can consider arbitrary subgroup. And then the G test measurement is basically a projector. So like when we output equal in our protocol, yeah, this is a projector onto trivial irrep onto this subgroup G of symmetric group, and unequal it's a complement. And we can just go and calculate again using representation theoretic tools the formula for the soundness probability of the protocol is arbitrary group G. And yeah, it turns out to involve such an expression where you can see, so k lambda sub mu is a Koska number, so it's a combinatorial number, which is actually quite difficult to calculate and to deal with analytically, fortunately. And the other ingredient is that what we need to know, we need actually to know the multiplicity of the trivial reducible representation of the group G inside arbitrary irreducible representation lambda of the symmetric group. Yeah, so this is a classical restriction problem in the group theory. And for some groups G, we can answer this rather easily, but for some, it will be a very hard problem, in principle. Yeah, and just, yeah, and again, the circuit still looks exactly the same as for permutation tests or for circle tests and so on. Instead, we will just need to use the Q of T of the size of number of elements in the group G. the ancillary register. Yeah, as I said, some examples. So G, if you consider the full group, this is just permutation test. Tn is a cycle test. And what we thought would be nice to do is to consider the following: iterated cyclic rest product subgroup. Well, why? It's because of the prime number position theorem. We can write any number right in the prime factorization. And in principle, if you can understand how to restrict such, how to restrict arbitrary irrep to trivial irrep of that group, that give us a formula for the soundness error shown in the previous slide. But for that work, this is very complicated question in general. And for this work, we assume that the number of states is a power of 2. And in that case, it's just an iterated swap tree test. So it actually looks like a tree. So we just apply like a bunch of swap tests in the tree manner. So this has like logarithmic in depth, which is nice. And it turns out that analyzing this test and finding the formula for the soundness is very difficult question. And what we were able to achieve so far is to lower bound this by some complicated recurrence relation, which actually achieves the scaling 1 over n on the hardest input. So in some sense, this performance of this test is the same as a permutation test on the worst case. And it would be actually interesting to find whether this test gives some advantages over the permutation test over wider class for assumptions for the input states. But as I said, that would involve understanding representation theory of this iterated rest product group to a higher level. Okay, so and what we can now say about some open directions. So here in our work, we didn't study the approximate version of quantum state identity. So this would be the most natural thing to consider now if we can prove the same optimality without one-sided error restriction for the permutation test. Yeah, as I said, it would be nice to analyze the G test further for the iterated RES subgroup, but also find some other interesting groups which would be interesting for certain inputs. Yeah, and the last question: can we actually use similar techniques to reconstruct this composition factor? So can we actually extract more information other than just saying they're equal or unequal? This and prove optimality for such protocols using the similar techniques. So with that, I want to thank you for listening.
Thank you for the talk. I'd be interested in your speculations about the approximate case that you mentioned in the end, because it seems like a very natural question. And I'm wondering whether you expect that the same kind of techniques apply, or is there something fundamentally different about the approximate version?
Yes, so yeah, we thought about it, and so we assume that in principle, if we can think about, yeah, so if we model our input with some kind of mixed noisy state, then I think we can we expect our techniques would go through basically. Yeah, so with this kind of model, we believe it can be done. Yeah, about other models, I don't know.
Okay, so then maybe I misunderstood what you mean by approximate version. So
yeah, no, by approximate I mean that maybe like we assume that our input state is some kind of mixed state, right? With high degree component, which satisfies the assumption, right? And some small component which doesn't satisfy the assumption. Yeah, if you want to, yeah, assume some kind of norm closeness, it's a bit tricky, so we don't really, we're not sure how to do that.
Hi, thanks for the talk. I just wanted to ask about a related problem, or at least what I think might be related with this like distillation of mixed states, like many copies of a mixed state. I know that there was a paper that kind of showed that this iterated swap test or something that looks like it is sort of optimal for that problem. I don't know if you're familiar with that problem, or if you think that they're similar, or if you think they.
No, I personally haven't thought in that direction, so maybe
Okay.
I can give a useful comment.
Okay.
Yeah, thanks for the great talk. Have you ever thought about what is the best soundness you can achieve in the like a product test or swap test kind of thing? Like you wanted to accept with probability like very close. I don't know. It's probably impossible to get it to accept with probability 1 if it's orthogonal. But and then as the states get closer together, then you wanted to accept with lower probability.
Yes. So like what we want to assume here is yeah, basically. So our hope would be, right, if we know so if we have this promise for mu, right, then yeah. So this would be like the formula for the soundness. But because you know, those numbers are very difficult to deal with, it's very difficult to understand the scaling symptotically. And so, but we would like to have that for certain choices of mu, that like some concrete choices of mu, this would scale similarly as the permutation test, basically. So if you can prove that, that will basically mean that our easier tests is also good for that kind of input. But this easier test has lower complexity kind of in implementing, so it would be good to use it in some context. That's kind of the way we are thinking. Was my interpretation correct?
I'm not sure like how so this how that was related. So I mean, I was more thinking about if you have like you don't care about perfect completeness anymore. You want to get the soundness as good as possible at the cost of the completeness.
Yeah. In some sense, yeah, we kind of asking the question because yeah, we are maximizing in the end. We are maximizing the average success probability, but it turns out that this maximization of the average achieves the perfect completeness almost all the time, basically. Yeah, the question we started from was, can we trade completeness for soundness in some sense? But it turns out to be not possible. That would be one of the outcomes, essentially, of our result.
Okay, thank you.
Thanks for nice talk. So for the swap test, it is known that you can do the swap test without ancillary, right? So I'm wondering if you can generalize this result for the G test. So for instance, if the G is in this specific form, you don't need the ancillary to, perform this kind of thing, or have you thought about that?
Yes. Yeah, I don't know if it's possible. Yeah, so, but it's a good question. Definitely worth thinking about. Yeah, I don't have a quick ideas. Okay. Yeah.
Sorry, before going to the next speaker, I've been told to say that the previous speaker is happy to accept questions via Discord. So, yeah.
it working? Should I put it higher? Or is better? Is that better? Yeah, better. Okay. And then what about a clicker? Or should I do it here?
You can do it here, but if you want the point to.
Okay.
Yeah.
This is the PDF.
Yeah, this is the
I think
PDF.
if we do the PowerPoint, it'll be bigger.
Oh, okay.
Yeah.
Can do.
Oh, it's okay. Yeah, because then I think it fills the whole screen, you know.
Yeah. Robbie will talk about learning with conjugate today and
Hi, everyone. Thanks for coming to the final session of the day. Okay, so today I'll be telling you about learning with conjugate states and quantum memory. So I'm sort of going to tell you the punchline in the first slide, and then we'll see how this situation arises. So what is the punchline? The punchline is there'll be a learning task defined on some unknown quantum state, which will come from an experiment or maybe a quantum simulation in a computer. And there'll be some well-defined learning task where if I'm allowed access to entangled measurements on the unknown state tensored with its complex conjugate state. So this is a state where I just complex conjugate every entry of the density matrix. So it's a well-defined quantum state. Then I can achieve this task with logarithmically many samples. However, if I don't have the complex conjugate state, even if I'm allowed entangled measurements on many copies of the original state, still the sample complexity is exponentially worse. So this was a surprise to us that there is such a task where this holds. And I think it shows how sort of rich and complicated the landscape of these learning tasks and resources are. So we're trying to sort of, I'll try to convince you that this complex conjugate state is really like a new quantum resource that you can use in learning. And which brings me on to my next slide. Again, before sort of starting with defining what our task is, how do we get this complex conjugate state? And the bottom point, so in general, it's not possible. So you should really think of it as a sort of resource that isn't always available. But sometimes it would be. What is two situations? So I guess I'm going from bottom to top here. So time reversal, certain systems, if I sort of negate the Hamiltonian and reverse backwards in time, then I can prepare the complex conjugate state for certain systems. So that's a sort of capability that would allow you to get this complex conjugate state. Alternatively, if I'm preparing my state that I'm interested in with a quantum algorithm on a quantum computer, then it's a simple matter of complex conjugating every gate in the circuit, and this will generate the complex conjugate final state. So if I'm using a quantum algorithm, then I have this resource available to me always. So right. But yeah, in some certain experimental platforms, it won't be possible. Okay, so with that, let's start the real talk. So we'll start with an outline of what is shadow tomography. Shadow tomography is a task of this form. And by the way, I always have to sort of remind people that it's not the same thing as classical shadows. So classical shadows is a particular algorithm to solve shadow tomography. But shadow tomography itself is not an algorithm, it's a task. So given copies of an unknown quantum state, we have a list of expectation values that we would like to learn. And we want each of them to precision epsilon. And the question is, how many copies of the quantum state do we need to consume in order to achieve this task? So you can think of these quantum states as an expensive thing. Maybe you need a quantum algorithm to prepare it, or you need to perform some experiment to prepare a single copy. So we'd like to minimize the number of copies that we need. And this sort of is an abstraction of a lot of tasks that people commonly face in experimental physics and quantum chemistry and all of these sort of different areas. OK, so this is just in words the same thing that was on the previous slide. This is the task of shadow tomography. We can point out a few sort of trivial ways to perform this. So one would be to measure one observable at a time, right? I have my first observable, second, third, and each one I need 1 over epsilon squared many samples to get to precision epsilon. So this gives me a sort of m over epsilon squared scaling. So linear in the number of observables. However, this is not great if m is very large. If the observables commute, then we can do this with log m over epsilon squared samples. Why is that? I have a very brief slide on this. So we can just measure in the simultaneous eigenbasis. And then I guess intuitively, this will make sense to everyone that you get information about all of these observables at the same time. But formally, you can just use the empirical estimates, and the Chernoff bound gives you this sort of guarantee. OK. Somewhat miraculously, Scott Aronson showed, when he introduced this task, that you can always get this log m scaling, which is extremely surprising when you first see it and counterintuitive. But he has some heroic sort of protocol that achieves this. There's 2 main caveats as to why this doesn't solve everything. And the 2 caveats are that it's explicitly exponential time. And the second caveat is that to perform Aronson's protocol, you need to entangle all of your copies of the quantum state and perform joint measurements on everything. So you can imagine why sort of, even in fault-tolerant quantum computers, this would be too much to handle. Because say if my sort of system is 100 qubits and what epsilon is like 0.001 or something, then 100 over epsilon squared is a lot of qubits, logical qubits that you need to sort of do this. So for these 2 reasons, this is more of a features as an information theoretic proof that it's possible to get this log m scaling in general, rather than something that actually will be run. OK. And I should also mention, I don't have a slide on this, but classical shadows is another thing which sort of attacks this problem. And that only works when the observables are either local or low rank. So it sort of doesn't work in general. OK, so as a sort of leading example, we can ask what happens with the shadow tomography task if I want to estimate all of the Paulis on my unknown quantum state. OK, so we sort of face this dilemma because these Paulis are not commuting. So there's no sort of nice basis that I can choose that sort of tells me about all of many, many Paulis at the same time. And in fact, you can sort of formalize this intuition. And in 2021, they showed that if I measure one copy of the state at a time, in fact, I need exponentially many samples in order to perform this task. Even just information theoretically, this was shown. However, it turns out that you can overcome this obstacle by using entangled measurements. So the insight here is that if I have a Pauli P, it might anti-commute with the Pauli P prime, but P tensor P always commutes with P prime tensor P prime, right? Like X tensor X always commutes with Z tensor Z. So there's some simultaneous eigenbasis on 2 registers of all of the P tensor P. It turns out this is the Bell basis. So if I measure rho tensor rho in the Bell basis, I can simultaneously estimate all of these trace of P tensor P times rho tensor rho, which is equal to trace P rho squared. So by just entangling 2 copies, I can get information about I can square root this and get trace of P rho, but I lose the sign information. But I can estimate the magnitude, at least, of all of these expectation values with logarithmic scaling, right? Which would be log 4 to the n, so linear in n. OK, So now I'll move on to talk about the displacement operators, which is the task of performing shadow tomography on the displacement operators. This is the thing where we see this exponential advantage from using the complex conjugate state. So what are the displacement operators? Here, we should imagine not being on a Hilbert space of n qubits, but rather on a Hilbert space, a d-dimensional Hilbert space, d to the d. But d, you should imagine, is very, very large. So d is exponential. For example, if I were to encode this Hilbert space on my quantum computer, then d would be equal to 2 to the n, right? So here, d is sort of growing exponentially. This is sort of the Hilbert space of my quantum system. Again, I have an unknown quantum state. And how do I define these displacement operators? Well, I can define x and z as written here. So it's sort of a d-dimensional analog of the Pauli's. X sort of shifts you around the basis, and z is sort of like a clock, right? It sort of applies a phase according to where you are. And then in general, we can start multiplying x and z together. And this phase is just a convention to get these sort of d sub q comma p. And q is how many x's we apply, and p is how many z's we apply. So one way to think about this is that there's sort of a discrete phase space parameterized by q and p, and d of q and p is a unitary that shifts you in phase space by q in position and p in momentum. Right? X is like a position shift, and z is like a momentum shift. OK, so the task that we look at is to perform shadow tomography on these displacement operators. So we want trace of d times rho for all of these. I guess there are d squared many of these displacement operators. So these are unitaries, so this will be a complex number in general, right? So, but it's still a well-defined task to sort of estimate all of these. OK, so now I will I can share what are the results. So the first two theorems are both lower bounds, and the third theorem is a new algorithm. So the first theorem says, this is just like analogous to the Pauli case, where if you measure one copy at a time, you need exponentially many samples. So the same thing holds here. If we measure one copy at a time, then we need linear and d samples. So that's sort of, not too surprising. Theorem 2 is a more surprising one. So even if I measure, rho tensor rho many times, up to k times, where k can be sort of pretty large, it depends on epsilon, right? Then still the sample complexity is lower bounded by the square root of d. So remember, d is some exponentially large thing. So this is still an exponential number of measurements that I need to make, even if I entangle many copies of the state. However, if I'm allowed to measure rho tensor x complex conjugate, then suddenly I can perform this task using only log d samples. So exponentially better than the previous two. OK, so how can this possibly hold? So first, we'll look at this theorem 3. How do we achieve this task using rho tensor rho star? And hopefully this will sort of make the intuition clear as to why this can be a useful resource. OK, so a little bit about these displacement operators. They have some commutation relations where, remember, if I braid two Pauli's, I either get a plus sign or a minus sign, right? They either commute or anti-commute. These satisfy a similar thing, but when I braid them, I can pick up a d root of unity, so a phase. And by the way, the thing that goes inside this is sort of called the symplectic product, if people have heard. And so you can imagine these things in phase space. It's sort of d is like a sort of vector that shifts you a displacement. And if I shift in that direction instead, that's sort of the transpose of the unitary. And then shifting the opposite direction is the inverse, as you'd expect. And then shifting down this way is the complex conjugate of the unitary. So this is sort of a nice picture. And what you can realize by looking at this commutation relation is that, so it's no longer true that D tensor D always commutes with D prime tensor D prime, right? Because if I braid the first two and the second two, it's not true that, before -1 squared was equal to +1. But here, I have a phase, which if I square it might not equal +1. But if I use the transpose unitary, then it is true that D tensor its transpose commutes with D prime tensor D prime transpose. Because I braid the first two, I get the positive phase, and then I get the complex conjugate phase when I braid the second two, and those cancel and give me a commuting set. Right, so there's some basis which simultaneously diagonalizes all of these unitaries, D tensor its transpose. What is this basis? I can get there by applying this very simple circuit. So I do a, I guess you should read this in reverse, right? I'm like, to prepare the basis going this way, so I do a quantum Fourier transform and then a controlled shift. So this is sort of the analog of how to get to the Bell basis for 2 qubits, right? Like a control shift and then a Hadamard. Okay, but then if I measure rho tensor rho like we did before, this sort of doesn't give me anything useful. It gives me trace of D times rho times trace of D rho star, if you sort of analyze it. But what if I measure rho tensor rho star in this basis? Then I get trace of D rho squared. So, this isn't a proof that it's impossible without rho star, but this sort of tells you, and how it happened was we sort of found this algorithm, and then we were thinking, oh, that's great, but I'm sure it's possible with rho tensor rho, so let's try and find a way to do it. But then we actually found a proof that it's impossible, so it was a bit of a surprise to us. So what is the proof sketch of these lower bounds? So you could define these E operators, which are sort of just permission versions of these displacement operators. And then you consider this collection of quantum states, rho sub Q, P, and R. So this will be the identity matrix, so the maximum mixed state, but shifted by an epsilon amount in the E, Q, P direction with an R as a sign here. So R can be plus or minus. And a task you can consider is distinguishing. So I either get a random one of these states, or I get the maximum mixed state. And I can ask, can I distinguish these two scenarios? So certainly, if I'm allowed, if I can perform shadow tomography on these Ds, then I can perform this task because I can perform shadow tomography, and if everything comes out 0, then I say I have the maximum mixed state. But if I see that one of the displacement operators has a high expectation value, that tells me which row I got from the ensemble. But it turns out that this distinguishing task is impossible using the restricted kinds of measurements that we saw on the previous theorems. So you can show that by saying that the even if I apply any combination of these measurements, remember they were sort of single copy measurements or measurements on row without the complex conjugate. No experiment, so L here is sort of the entire history of such a protocol, and it can even be an adaptive one. And you can show that the total variational distance on the maximum mixed state versus on a random one of these states doesn't differ enough to statistically distinguish the two. So that's how we show this. Okay, so how does this fit into a bigger picture? Okay, so the first thing is that these displacement operators don't come out of nowhere. They are sort of the natural operators that you see when you consider a discretization of a bosonic system. So if you imagine this Q and P being continuous, what we get is precisely a bosonic mode, like a single photon or et cetera. And you can actually phrase this learning algorithm entirely in terms of optical sort of bosonic language, which I had to learn. I didn't know it before this project. So, you can take rho tensor rho star and apply this entangling Gaussian rotation. They call it a Gaussian rotation because it's e to the something quadratic. And then you perform measurements on the first register in the Q quadrature and the second one in the P quadrature. And these are called homodyne measurements. And you probably know what this means better than I do. And this sort of gives you outcomes which are entangled on the two copies. So you get sort of Q1 plus Q2, where Q is position, and then E will be sort of a momentum entangled measurement. And we can sort of perform the same task on a bosonic mode. And this is interesting because, for example, these displacement operators are important in GKP code states, right? These are the things that stabilize GKP code states. So maybe this could be an interesting sort of way to probe these sort of interesting bosonic states. A question for the audience: how can we formalize these lower bounds, right? These sort of D-dependent sample complexity lower bounds in the case of a continuous bosonic mode? I don't know how to do that. Okay. And this is the final slide. I'll just say that I think this is an exciting research area because what it really asks is, what can I learn about a quantum state by exploiting quantum memory, right? So, in a conventional sort of physics lab or experiment, I'll sort of get my quantum state. Somehow I'll cool down a condensed matter system, or I'll, perform some optical experiment, and I'll get an entangled quantum state, and then I have to measure it, right? I have to sort of, it hits the sensor, and I measure in some basis. This is sort of the conventional way that physics is done. But if in the future we have quantum computers, you can imagine doing physics in a very different way. You can imagine, sort of in the nearer term, you can imagine preparing an interesting quantum state with a digital quantum algorithm, right? In which case we can do this in parallel with multiple copies and then measure them together, right? Alternatively, even further in the future, we can imagine performing a physical experiment and then transducing the quantum state coherently into our quantum memory, and then doing it again and waiting for the next copy, and then measuring them in an entangled basis together. So that's the even further sort of future application. So, the question is, what can we do with these entangled measurements? And this is a new type of quantum advantage, right? This is not in the same sort of paradigm of what problems can we get computational speedups. It's a different type of advantage, right? It's an advantage of using quantum memory to learn about unknown states. And all of the sort of practical examples of this rely on this trick that we saw in this talk. So they rely on this trick where we sort of extend the Hilbert space by tensoring a different Hilbert space, and then we make the operators commute. And then we measure in their sort of new simultaneous eigenbasis. So, and then we managed to prove this theorem, which says that roughly this trick only works for things that look like displacement operators, which is what we tackled in this talk. So it's sort of the maximal application of this trick. So I guess what I'm saying is, for the audience, we should go out there and find new tricks that we can use to exploit quantum memory. And I don't know what they'll look like, but I think we need to go beyond this sort of the one that we used in this talk. Okay, I'll finish there. Thank you.
Thank you for the wonderful talk. So my question is about how you get raw star. So yeah, there is a literature about how you can do with a supermap transform a given unitary into a conjugate unitary, and there are results proven that you need to have basically order D number of samples of such a unitary. And so my question is, have you considered trying to analyze this question, but not for the whole set of unitaries, but maybe for some restricted subset or like a submanifolds and things like this, which can lead to lower than D scaling, basically, like logarithmic in D scaling?
Yeah, I don't know, but I think in general, it's definitely true that it's impossible, right? I think you can probably In fact, I mean, it must be, otherwise our theorems are not true. So, it's impossible in general. But I would say a very interesting sort of very general case where you can construct the complex conjugate is if you have this, what Rob and Cathari would call the source code, right? You have the circuit description of the unitary. So if you have the source code, then you can easily implement the complex conjugate unitary.
Thanks.
Yes, thank you for the talk. So in theorem 3, so this algorithm you gave, is it actually also known to be optimal, like in terms of sample complexity? Or can maybe do something, hope for something better even?
Yeah, thanks for the question. So log D is optimal, but I don't know about this epsilon to the 4. Now, where does that come from? That comes from the fact that what I'm really estimating is trace of D rows squared, right? So when I square root that, I would usually get, if I'm taking samples, like flipping a coin, right? I get an estimate of the bias with 1 over epsilon squared samples. But that becomes, when I do the square root, 1 over epsilon to the 4. Now, I think it's a very interesting question whether that is fundamental or whether that can be improved. So this epsilon to the 4 is sort of, maybe could be, the only lower bound we have is epsilon squared, to my knowledge. Yeah. Right. Right, but that's right. But also, interestingly, in Scott Aronson's shadow tomography, he had epsilon to the 12 or something crazy. But the best known shadow tomography is epsilon to the 4. So, yeah.
Cool, thanks. Thanks for the nice talk. Yeah, in this slide, maybe I missed something, but do you study like the regime where D is big, but you have like a less number of observables? So like the number of observables in your
That's right. So I'm saying I want all of them. So there's D squared many. Yeah.
But can you get like the number of observables, or it's just like
it's D squared.
No, if it's I have like K observables much lesser than D squared, like two or three observables like this.
Well, if I pick a commuting set, then it's quite easy. For example, so it depends on the set.
Okay. I was expecting like a log minimum of log D, log K, the number of observables.
No, I mean you can't show that because if they're commuting, then.
Thank you for the nice talk. So one of the premise that we are interested in calculating expectation values for polys is, well, they arise naturally in Hamiltonian simulation algorithms, or, well, you can decompose any operator into a poly basis. So these displacement operators, do they arise in computational problems?
Well, that's what I was saying at the end. They sort of correspond to a natural set of operators on like a bosonic, on a discretization of a bosonic system.
Okay. So these displacement operators form a basis on the set of operators as well?
That's right.
Oh, okay, nice.
Thanks for the talk. So I wonder if it would be possible to find an advantage similar to this, but in a task like doing tomography in fidelity distance or trace distance.
Right. As in a conclusion like where you can exploit the complex conjugate state?
Yes.
So I think a friend of mine told me that measuring the overlap of a state with its complex conjugate is something you can do very easily if you have the state and its complex conjugate, but is exponentially hard if you don't have the complex conjugate. So that's sort of a fidelity type task. But it was really sort of, we wanted to show for a natural sort of shadow tomography task that it's useful.
But what I mean is if you can think of exploiting this structure in doing tomography with respect to the trace distance, like the usual tomography.
I see. I'm not sure if it would be helpful or not. Yeah.
Okay.
Hello? Yeah. Thank you very much. Just wondered, in this case, for example, this is still one boson, right? So it's not, so it's basically something we could also imagine classically. You just have basically a P and a Q, right? So I don't think there is a lot of applications of this case as well. Is it correct? Or?
Well, okay. I mean, one boson can be quite complicated because it's infinite dimensional.
No, I know, but you just need to compute one integral, right? It's a very low dimension in my mind. You do not want exponentially many. I'm not sure. I'm just trying to think about an application.
I think like this D sort of corresponds to how much you discretize.
That's right.
Some sort of energy cutoff, right?
Yeah.
So like it's sort of like if I have a harmonic oscillator or something, I'm going to more and more energy levels if I have a higher D. And so I'm sort of resolving more and more higher frequencies in phase space. Maybe that's
okay. Makes sense. Thank you. And maybe just another clarification. So you can compute the trace squared with your trick. So is it correct you cannot get the sign, or do you understand?
That's an interesting story, and we actually have a sort of separate paper that's all about that. You can, although there's a lot more caveats. It's not as nice. For example, sometimes it's not. We don't know how to do it computationally efficiently. So sometimes we only know how to do it if you spend exponential classical pre-processing, or sometimes in certain situations we know how to do it, but the epsilon scaling is like really bad. So I think that's a really interesting question, and we looked at it, but it's not solved by any means. But the short answer is yes, we can do it. Yeah.